Hello everyone once again. Well, shall we start? 1 minute to go, it appears. Shubham Jaiswal. Great. Well, so here we go. So we were discussing about this. Okay, we can start, no? Can anybody just tell me?
Yes, sir.
Yes.
You can see my this the screen which is shared
Yes,
with
sir.
you. Okay.
Yes.
Well, so I was discussing about the failure of the gear tooth by pitting or surface fatigue failure, right? And we have briefed upon this when we discussed about different types of gear failure or gear tooth failure as such. So this is going to happen. Okay, so now if you look at this particular diagram here, okay, so this is a point, you can say near to the pitch point along the pitch circle diameter, which will come in contact with the other tooth or meshing tooth time and again. So there are chances that this particular portion is subjected to high contact stresses, and therefore there is a chance of pitting or removal of small amount of material from that particular portion, right? So that small removal of the material leads to sort of crack initiation. Okay, if you look at this particular diagram here, crack is initiated, and because there is a lubricating oil, there may be some corrosive effect, and the crack propagates. Okay, and after some time, there may be spalling of metal. Spalling is nothing but again breaking away of the small amount of material from the tooth profile. Okay, so and this leads to destructive pitting, something called as destructive pitting. Okay, and the tooth failure, or that leads to failure of the tooth. Okay, so in order to avoid this type of failure, we need to ensure that wear strength of the gear tooth should be more than the effective or dynamic load acting on that particular tooth. Okay, so that is what is requirement. So we have seen in the previous lecture that we can actually take care of beam strength by ensuring that beam strength is greater than dynamic load. Now we are looking at second type of failure of the tooth, and that is on the basis of wear strength. Okay, so here we are going to ensure that wear strength of that tooth, which is subjected or which is in mesh with other gear, is more than that of the dynamic load. Okay, so now before we discuss about wear strength, I will spend some time on the Hertzian contact stresses. Okay, so So here if you look, why we are talking about Hertzian contact stresses? Because contact is one of the most common methods in transmitting forces in a machine. And when elements of machine make contact with each other, a pair of equal and opposite forces is generated according to law of action and reaction. Right? And typical example is this meshing of the teeth in case of gears or rolling contact bearing. Now, theoretically, when contacting surfaces or curved contacting surfaces come into contact with each other, the contact is defined by a point or line. If you see here, in this particular diagram, in this, right, you see here, say, right circular cylinders, which are in contact at this particular line, along this line, due to the force acting on both sides, that is capital F. Okay, so at this particular point of contact, theoretically we can consider this line as a point of line of contact between these two cylinders. And when this type of contact happens, contact stress will be developed at the small area, because that small area will be undergoing a deformation. So, or you can say it will deviate elastically from their normal curve. Okay, so there is a deformation at the point of contact, and because of the deformation, and that area of deformation is very small, high contact stresses will be developed. Okay, so we are going to further discuss about that. Now, as I mentioned, we are going to take care of contact stress on the basis of theory proposed by Hertz. So Hertzian contact stress refers to the localized stress that develops as two curved surfaces come in contact and deform slightly under imposed loads. And the magnitude of this contact stress depends on material properties, geometrical dimensions, and applied loads. Generally, small radii lead to small contact areas, and because the contact area is small, the contact stress is very large, as shown in the previous diagram. And the induced contact stress is three-dimensional. Okay, so if you go back to the previous diagram here, okay, so this contact stress is sort of three-dimensional. Okay, so if you look at this deformation, it can be characterized by a stress which is perpendicular to this surface, contact surface. Okay, so therefore there are so many lines are shown in upward and downward direction here, arrows. These arrows indicate the contact stress, and which varies from say minimum value to the maximum value, minimum value at the periphery to the maximum value on at the center. Okay, so it is characterized in that way. And this particular contact stress theory was used by Earl Buckingham in determination of wear strength of the gear tooth. Okay, so Earl Buckingham has contributed a lot by giving precise equation for how to calculate the dynamic load, and also he has given analysis for the wear strength. So we are going to study his analysis now in maybe next 2 to 3 lines slides, maybe 5 slides you can say. So what are the assumptions when he performed this particular analysis? So contacting bodies are elastic, isotropic, and homogeneous. That is the first assumption. Then the cylinder radii are very large when compared to the width of the deformation. I will explain what is meaning of width of deformation on the next slide. And the contact is frictionless. So with these three assumptions, we go ahead with the derivation for the beam strength. Wear strength of the tooth. So if you see the side view of the contacting cylinders, it looks like something like this, which is resembling to the gears. Now, in case of gears, I have shown this contact area, which is very small here. Okay, and then if you see, there is a variation of this contact stress from minimum value of sigma to the maximum value at the center, and exaggerated portion of this contact is shown in this, and we see clearly that it's a sort of elliptical, right? So the contact stress according to Hertzian theory between two cylinders which are pressed together as shown in this figure is given by this equation here. Sigma c is equal to twice f upon pi bl. Okay, so we are taking directly that particular equation from Hertzian analysis. We are not going into details of that, how he has arrived at, but we can say it is force upon area. Okay, so area is elliptical, and if you consider half the radius of this, okay, it is b, and we can consider the instead of ellipse, we can consider it as a circle, and circle is that is a circular beam of length L. So in that, what do you say, approximation we can consider, but actual expression sigma c is equal to twice f upon pi bl, we need to go through how Hertz has arrived at it. And here this b, now we should not confuse this letter b or nomenclature b which is used here. Now the b which is used here is actually, Mayur Gaikwad has raised hand. Yeah, can you tell me, Mayur? Mayur, you want to say something?
No, sir, no.
Okay, that's fine. So B is the length of the deformation when the cylinders are in contact. We should not confuse this B with the face width of the gear. Okay, that will come into picture in the analysis in due course of time. Now again, if you consider this equation by Hertz, sigma c is equal to twice f upon pi bl, and this length of deformation is given by this particular expression, twice f into 1 minus mu square into 1 upon e1 plus e1 upon e2 whole divided by pi into L into 1 upon d1 plus 1 upon d2 raised to half. So it is under root. All these terms are under root. So sigma c is the maximum value of the compressive stress. F is the force pressing the two cylinders together. B is the half width of the deformation. So we have assumed that total width of the deformation is twice B. L is the length, axial length of the cylinders. D1 and D2 are diameters of the two cylinders. E1 and E2 are moduli of elasticity of two cylinder materials, and mu is the Poisson's ratio. Okay, so these two equations we are taking as it is, and we are moving on. So from these two equations, what I showed on the previous slide, by substituting B into sigma c equation, we arrive at equation C as shown here, right? Where R1 and R2 are radii of two cylinders. Now we know generally in most of the cases when this Buckingham actually come up with this analysis, obviously gears were made of the metals, and that too mostly steel. So in that case, substituting Poisson's ratio, which is close to 0.3 for steel, okay, so we get this particular constant 1 upon pi into 1 minus mu square as 0.35, remaining parameters as it is. So we get sigma square is equal to this equation D, right? Very straightforward. There is no difficulty in that. Now on this slide we are going to have a connectivity between that Hertzian contact and how the gear tooth are in mesh. Okay, this is very important. Now if you look at the pair of gear teeth in contact as shown here, this is the we can consider this as pinion, therefore radius is dp prime by 2. This is gear which is having radius as dg prime by 2, and the gears are in contact, and this particular point is a pitch point wherein pitch circles are in contact, and it is along the line of action also, right? So the contacting cylinders which I had shown on the previous slide are actually can be considered as cylinders which are having radius r1, that is from here to here, and radius r2, that is from this point to this point. So these radii are considered as the radius of curvature of these tooth profiles at the pitch point. Are you with me in this? Because here we are actually correlating contacting surfaces with the how are we going to accommodate that contact stress in the analysis of wear strength of the gear tooth. Okay, so what I'm saying is that, once again I repeat, okay, so at pitch point we are assuming that the surface pitting or surface failure is going to happen near the pitch point. Therefore, we will because tooth profile is involute. So at pitch point, if you consider radius as contacting cylinders, so we can have R1 as the radius of, if you draw a line, circle like this here, that is one circle here, and with R2 as radius we can draw another circle here in this way. Okay, so these two cylinders are in contact here. So this is the contacting force is resultant force between pinion tooth and meshing tooth on the gear, right? So because R1 and R2 are the radii of the contacting cylinders, and we don't know right now in the analysis of this gear what is magnitude of this R1 and R2, but using geometry or trigonometry we can convert this R1 and R2 in terms of radii of gears, pinion and gear here. So that is in terms of dp prime by 2 and dg prime by 2. So if you look at this triangle, from center of rotation of the pinion to this pitch point and to the center of this particular cylinder which we have assumed here with radius r1, so we consider this particular triangle. Okay, and we know this alpha is the pressure angle, which is also can be considered as, if you draw horizontal line or tangent line, common tangent for these two pitch circles and this line of action. So angle between these two lines is alpha. That is same angle will be between the vertical and perpendicular line joining these 2 points, center of this particular cylinder which we have assumed here and center of rotation. Well, so we want to convert this R1 in terms of preferable dimensions as say radius of gear. So sin alpha, we can make use of sin alpha is equal to R1 upon this length, that is dp prime by 2. Therefore we get this R1 as dp by 2, dp prime by 2 into sin alpha. And similarly, by making use of this triangle here as shown, I'm just tracing the lines of that triangle here. From this again we can consider sin alpha is equal to R2 upon dg prime by 2. So R2 is equal to dg prime by 2 into sin alpha, right? So we get these relations, and now this is the point where we are actually making use of that contact stress by Hertz into analysis of wear strength for the gear tooth. Okay, so this geometrical relation is very important, and we substitute R1 and R2 magnitudes back into that contact stress equation. Okay, so we'll move on to the next slide. Hope there is no doubt or difficulty as of now. So in that equation for sigma c square, we have one bracket as 1 upon R1 plus 1 upon R2. So we substitute R1 and R2 as found on the previous slide, and we get this particular expression on the right hand side. Now this particular expression of inverse of addition of the pitch circle diameters of pinion and gear, we want to put it into more acceptable expressions. So what Buckingham did, he defined one factor called ratio factor as Q is equal to 2ZZ upon ZG plus ZP. So again we can convert in by, we know relation between number of teeth and pitch circle diameters, so we can convert this Q in terms of pitch circle diameters as shown here by this expression, and we can further write this particular expression into bracket 1 upon dp prime plus 1 upon dg prime as this, and when you substitute for Q, we end up in this equation. So 2 upon Q into dp prime, where Q is ratio factor as defined like this. Okay. Now again, as far as Q is concerned, if you divide the numerator and denominator by ZP, that is number of teeth on pinion, we consider this as 2 into ZZ upon ZP, which is I, that is gear ratio in that stage. Again we have ZZ upon ZP here, that is I, plus ZP upon ZP is 1. So this can be also written as 2I upon I plus 1, which is actually mentioned in the data book. Okay, so now we have expressions or equations G and E in front of us. Combining these two, we can express the radii of the contacting cylinders in the form of ratio factor, diameter of the pinion, and pressure angle as shown here. Okay, so we arrive at 1 upon R1 plus 1 upon R2 as this. Okay, now you substitute back this particular expression into the expression for contact stress, and also in contact stress there is a force F, and in our case that force is nothing but the force along the line of action. So we consider that resultant force along the line of action as Fn. So it is here, and as I mentioned, axial length of the gears is face width here. Okay, so L is the axial length of the contacting cylinders, whereas in case of gears it will be the face width, that is axial length of the gear. So L we substitute as B. Now again, as I mentioned on the previous slide, that this B, what we are assuming here is the face width of the gear, whereas the expression B which was mentioned in the expression for contact stress, that was deformation length. Okay, so you should be clear about this. There shouldn't be any confusion about that. Now substituting all these expressions what we have just now seen or arrived at into equation for contact stress, we arrive at equation for contact stress as this: sigma c square is equal to 1.4 Fn upon bq dp prime sin alpha into 1 upon E1 plus 1 upon E2. Okay, now rewriting this equation for Fn. Okay, so we can write Fn is equal to sigma square into whole denominator on this right hand side or left hand side divided by 1.4. So we define one load stress factor K as this: sigma square into sin alpha into 1 upon E1 plus 1 upon E2 divided by 1.4, and we can modify the previous equation for Fn as this. So Fn is equal to B Q dP prime into K. So here we can see we have arrived at a similar equation as that of the beam strength, but here we are considering wear strength as the design criteria. Okay, so we are saying that this Fn is proportional to sigma c or this K in the form of sigma c. Okay, other factors like B, Q, and dP are related to geometry of the gear, so therefore we can consider them for a given pair of teeth in contact as constant. So we can say Fn is proportional to sigma c square. Okay, because K has sigma square in it, and other parameters also, sin alpha, E1, E2, they are also constant for a given pair of teeth in contact. Fine. Any doubt till now? Any difficulty? Okay. Well, I will take you through this slide. It is similar to what we considered in case of beam strength. So the equation M1, that is for Fn, gives relation between the resultant force Fn along the line of action and the corresponding contact stress sigma c or load stress factor K. With increasing resultant force, the contact stress will also increase, and pitting occurs at a contact stress sigma c when it reaches to the magnitude of surface endurance strength. Now this is another very important statement. When pitting will occur when the contact stress value sigma c reaches the surface endurance strength, and the corresponding magnitude of Fn, corresponding in the sense the magnitude of Fn corresponding to what is magnitude of sigma c when it is equal to surface endurance strength is called wear strength. Okay, so therefore the wear strength of the maximum is the maximum value of resultant force that the tooth can transmit without pitting failure. Okay, it is on the similar lines what we said in beam strength. We said that beam strength is the maximum value of tangential load on that gear tooth that the tooth can transmit without bending failure. Here we are saying it is without pitting failure, right? So because we have said Fn is Fn value corresponding to surface endurance strength is the beam wear strength, we will replace Fn by Fw. Okay, so replacing Fn by Fw in the previous equation which was discussed on the previous slide, we write Fw is equal to Bq dP prime K. Okay, so this is the equation for wear strength of the gear tooth. And now next part in the design is we will prove that wear strength of this particular gear profile or gear tooth is greater than the dynamic load. Okay, so once we prove it is safe in this case, excuse me, then we can say the design for this particular stage, that is spur gears in that spur gears in mesh, is complete. Okay, so for that purpose we will make use of the equations which are shown on this slide from data book PSG 8.51. So we will make use of this k expression which we have already seen how it is to be derived. Then I have explained about why q is equal to twice I upon I plus or minus 1. Minus is considered for internal gears, so it is not, it is out of context here because we are not going to design internal gears. So Fw is equal to d1 instead of dp prime. Now in data book it is mentioned as d1, so it is diameter, pitch circle diameter of the pinion. Q is ratio factor, we can find it from here or on the basis of number of teeth on the both the gears. K is the load stress factor which is defined here. B is the face width. And we say design is safe when this Fw is greater than or equal to dynamic load Fd, right? So we'll move on to the next slide that now we are going to check design for wear strength. Okay, so the very important step when we are going to check it for wear strength is to find out what is the sigma c value. Okay, so design surface stress or contact compressive stress for the materials which we have selected. So we will go to page number 1.8.16. So I expect all of you to open that page. Okay, so 1.8.16. So here if you go to gears again, design stresses, we'll go there, but that is 8.5. so anyways I will just scroll down. Well, so we are going to page number 8.16. Yeah, here we are. Well, here we can see a table where it shows design surface or contact compressive stress, how to find out this value, and into square bracket that means design value, sigma c, design sigma c. So sigma c is equal to cb into hb into kcl in kgf per centimeter square, where cb or there is another equation is equal to cr into hrc into kcl. So these two relations are on the basis of Brinell hardness number or Rockwell hardness number. Okay, so cb or cr are coefficients depending on the surface hardness, and we will be in a position to find out it from table number 16, which is just below it here. HB or HRC is the Brinell or Rockwell hardness number, and KCL is light factor, similar to KBL it is. So we will find it from table number 17. Okay, so let's do it, this exercise. We have selected material for pinion as 40 CR1, and we have assumed that the Brinell hardness number is less than 350, right? So here if you look at this table 16, carbon steel and alloy steel for of any type, normalized or hardened and tempered, and we have considered similar sort of material here. HB is less than 350, we consider CB is equal to 25. So write down this from table 16, page number 1.8.16, the value of CB as 25. So write down that. Again we are running out of time in 10 minutes. Achha. So we have 10 minutes to go. Okay, well, so let's see how much we can finish off in 10 minutes. If meeting closes without any notification after this, that's fine. we will meet again next week, next Monday on this same platform. Well, so we will find out now what is sigma C, design sigma C. Now I will go to the code again. So let's see here. I have done, okay, I have not done that. So we'll write it sigma C. Okay, I will write here. You also do that. Sigma C, design sigma C is equal to, what is that equation? Are we with me? Are you with me? Anybody, any response? Hello?
So
Okay, so write down this equation. Sigma C design is equal to CB into HB into KCL. Okay, so I'm writing it here. So it is CB into HB, right? Into KCL. Now, in this code, I need to actually define these values before I use it. So I have HB for pinion. I think we have considered it as HB1, and it is already available in this workspace. I will see this HB1. Okay, so we have found out difference of HB. So it must be, yeah, it is there. HB1 is 283. So I will consider that HB1 for pinion as 283. KCL we need to find out and CB we need to find out. Just now I explained the magnitude of CB is equal to 25 from table number. So I will just, I will not print this. So magnitude of CB is, we can write here table 16 PSG 8.16. What is magnitude of KCL? We'll go to the data book again. So here we see KCL is mentioned on the, from the table 17 we'll find that. Okay, so here it is on page number 8.17. It is similar to KBL actually. It is live factors. Okay, but for wear strength, and KBL is for bending failure, live factor for bending failure. So again, we have material as steel, HB is less than 350, and we will assume life in number of cycles as more than 10 raised to 7. So KCL is 1. So I will write here. Well, though KCL is 1 here, you need to show that you have actually referred the data book and find out this value of KCL as 1. Okay, so here I will mention table 17 PSG 8.17. Okay, now we know these values. Can you tell me what is the magnitude of sigma C? Similarly, we can find out what is the magnitude of sigma C. Now this is sigma C for pinion, so I'll write it as sigma C1. And we also write down sigma C2, that is equal to, now again we will make use of the same methodology, and I think only HB value will change here. So I'll just copy paste here. So instead of HB1, it will be HB2 with other factors remaining the same. So can anybody tell me what is the magnitude of sigma C1 and sigma C2? Obviously these values are in terms of, or unit of these values is kgf per centimeter square.
Yeah, 7075 sigma C1.
Sigma C1 is 707. I will just run this again, this portion of the code. We'll see. Well, 707 kgf per centimeter square. Okay, so here HB. Okay, so let me just see in the data book. Yeah, it is in kgf per centimeter square. Okay, so we have calculated sigma C1 and sigma C2, 7075 kgf per centimeter square and 6025 kgf per centimeter square. Okay, so now we have design values with us. What is the next step in that? Step number 5. Find modulus of elasticity E1 and E2. Now because it is a steel, both materials are steel, plain carbon steel as well as alloy steel. There may not be much difference in value of E. So we will consider E1 equal to E2. So let's go to page number, what is that? In materials. Okay, in materials we'll see the physical properties of metals. Okay, page number 1.1. So here we can see there are different steels. Okay, so magnitude of elasticity, modulus of elasticity is 2.08 to 2.04 into 10 raised to, what is that?
So which page number?
It is 1.1, data book 1.1. It is 10 raised to 5. Okay, so we'll consider this as 2.08. Okay, so many times here, instead of going to page number 1.1, you know, many of you know what is the magnitude of E for steel. So that is considered as 2 into 10 raised to 11 Newton per millimeter square, right? Or Newton per meter square. Okay, so it is 200 MPa, right? Anyway, so you can make use of that also. Whatever value you can assume that value, or straight away from here you can consider it as 2.08 maximum value possible into 10 raised to 5 Newton per millimeter square. So we will consider this. Okay, so I will write here in the code. Now E1 is equal to 2.08, 10 raised to E raised to 5 is 10 raised to 5. Okay, and I will consider E2 is equal to E1. Okay, so that is there. Now after this, but this value is in Newton per millimeter square, so you will have to multiply by 10 raised to 2, right, to convert into kg, Newton per centimeter square into kg. So I think you will have to multiply by 10 raised to 3 to convert. No, it is the Newton per millimeter, so Newton is divided by, so multiply by 10 essentially, right? Right, multiply by 10 for converting E1 into kgf per centimeter square. Is that right? If I, by chance, if I commit some mistake, please be careful about that. Let me know if there is any mistake. I think it is correct. So this value multiplied by 10 is in kgf per centimeter square, whereas only 2.08 into 10 raised to 5 is Newton per millimeter square. So meeting may end at any point of time, maybe 1 or 2 minutes more to go. Now what is the next part? Find ratio factor Q. Okay, so I know I1, so I will just write ratio factor as, again it is from data book, we can find out, I will show where it is in data book. It is on page number 8.51. so we'll go to this Lewis and Buckingham equations for spurs. So this is page number 8.50. Yeah, so we'll go to 8.51. so you see here Q is equal to 2I upon I plus 1 we'll consider for external engagement. Okay, so I'll write here ratio factor Q is equal to 2 star I1. I will consider I1 because we have defined I as I1 initially, divided by